Okay, so let me begin by thanking the organizers for doing this wonderful job of organizing this meeting year after year. Okay. So I'm going to talk about something that we've been doing for the last 2 to 3 years. So it involves something called this spacing ratio or level spacing ratio, which I'll define as we go along. So this is something that's emerging to be widely used in random matrix theory as an alternative to something what is similarly known, which is basically simply the spacing, level spacing itself. Okay. So since it's used in random matrix theory, and in which case it will also be used in all the areas where RMT is widely used, such as in nonlinear dynamics as well as in condensed matter physics, so especially in areas that's broadly called complex quantum systems. Okay, so let me just start with a very brief overview. So the story starts, at least as far as physics is concerned, in 1950s, but RMT was known even earlier. So the idea then was that you have these nuclear levels, you had experimental levels which need to be understood. So one way of doing that, or to make sense of those levels, was the idea was given by Wigner, namely that the spectral fluctuations, so instead of looking at the levels themselves, you simply look at the spacings between them, which you call fluctuations. The spectral fluctuations of simple level sequences, basically desymmetrized spectra, are identical to that obtained from random matrices. So which essentially is a statement that says that random matrix theory can be used to describe spectra from many body quantum systems. So that was the story until about 1983, when Bohigas, Giannini and Schmidt conjectured that you don't need really many body systems. You can actually make do with even a single particle, but in a nonlinear potential, such that the system is chaotic. Even then the spectra of chaotic systems would have identical spectral fluctuations as that from random matrix theory. So the lesson is that RMT can also be applied to few body systems. So here is what Wigner's sum tells us. So let's say that these are the transformed levels that I have, epsilon. So you have raw eigenvalues coming from some operator. You transform them in some ways, and this is your spacing. So Wigner's sum basically predicts that under certain conditions you will get this form of spacing distribution, which is given by this. So the important physics part here is to say that such levels are correlated. So there are level correlations in them, as opposed to the case for integrable systems, where if you define the same kind of level spacings, what you will get is this e power minus s form, in which case the levels are uncorrelated. Okay, so let's see in a real case. So here is what I show is two figures from this paper. This is for entanglement spectrum. So which means that what you have is this collection of Schmidt eigenvalues obtained by doing a Schmidt decomposition for a many body Hamiltonian system. So this is the case where the parameters of the system are set such that it is in the thermal phase. So you get a very good agreement with what would be called the Gaussian orthogonal ensemble, or simply the Wigner's sum. On the other hand, if you choose the parameters such that it lives in the many body localized phase, in which case you get this e power minus s form. And as far as few body systems are concerned, so there are these very well known results for last 30 years. So this is the rectangular billiard, simply a rectangular system with a particle, and its dynamics is known to be integrable. So you can see that the histogram of spacings is very well described by e power minus s form. On the other hand, if you convert your rectangular billiard into a stadium billiard, you get a very good agreement with Wigner's sum. So these have been explored numerically and experimentally, and there is enough evidence for all these spectral fluctuations. Now there is a problem here. To be able to do any analysis of this kind, whether with many body or with few body systems, you need to do this additional process called unfolding the spectrum. So given that you have these kinds of levels, the raw levels which you would compute from any operator, you need to transform them to this epsilon 1, epsilon 2, epsilon 3 and so on, and this is the associated level density corresponding to, let's say, this levels, and you want to transform it in such a way that the level density of the transformed eigenvalues is a constant. So pictorially, if this is my energy axis and these are the levels, I want to move to this kind of distribution of transformed levels. Okay. So in fact, in the morning there was a reference to level density of random matrix theory, basically the semicircle. So typically in real physical systems you don't get a semicircle. What you will see is that as energy increases, the levels basically crowd up. So to make any statement about spacings, you need to put them on sort of equal footing, which is basically what this unfolding does, and which means that you need to know the level density in the first place, which is not easy to compute except for some special cases, but most of the time it can be done numerically, but then it's a fairly ambiguous procedure. And there are many results about the ambiguity that's associated with unfolding. So as an alternative to this spacing is this idea of spacing ratio. So which means that you take, so for instance, if I had these three levels, so this is Si is one spacing, Si plus 1 is another spacing, so you take the ratio of these spacings, and locally you could always assume that your level density is approximately uniform. So in this case you don't need to do any unfolding. So you can directly work with the raw levels that you would get, maybe from diagonalization or even from experimental data. And about 5 years back, RMT averages for spacing ratio distributions have been worked out. So here I would like to point out this beta physically corresponds to saying that that's the degree of level repulsion, and it takes values 1, 2 and 4 corresponding to orthogonal, unitary and symplectic ensemble of random matrix theory. Okay, so the question we were asking is what about the higher order spacing ratios? So one reason for looking at higher order spacing ratio is those are measures of long range correlations in the spectrum, and if you are a person working in dynamical systems, especially with Hamiltonian systems, you can figure out the limits of RMT descriptions from these long range correlations. So basically I wanted to find out what is the distribution of, let's say, the kth order spacing ratio, which is defined like this. So here I have just shown the second order spacing ratio. Okay, so let me show the central result. So again, this result holds good for Gaussian and another class called the circular ensembles of random matrix theory. So all it says is that the kth order spacing ratio distribution is simply equal to the first order spacing ratio distribution, but with the modified value of this index beta. So the original index beta corresponds to 1, 2, 4. It's called the Dyson index, and the modified beta prime is given by this formula that we have. K is obviously greater than 1. If you put k equal to 1, it's just an identity. Okay. So it corresponds to saying that if I want to find out the k equal to 2 spacing ratio distribution, let's say for circular orthogonal ensemble, which corresponds to Dyson index beta equal to 1, that will be distributed as the nearest neighbor spacing ratio distribution of what is called the circular symplectic ensemble, corresponding to beta prime being equal to 4. And this is only a special case of this more general result, but even more special case was already known at least for 30-40 years, namely that k equal to 2, just the spacing distribution itself. So if you take alternate levels and take its spacing distribution, that is simply the distribution coming from the symplectic ensemble. This is the result due to Mehta and Dyson. Okay, so these are numerical verifications of our scaling result. So not only from the numerically simulated random matrices, but also from many body systems. So what you see here is the histogram coming from the data, and this continuous lines basically are the ansatz that we have. And it also works with the experimental levels obtained from nuclear resonances. Okay, so basically the summary is that we have obtained a very powerful scaling relation that relates higher order spacing ratio distribution to nearest neighbor spacing ratio distribution, but for a different value of Dyson index. And it works for chaotic systems, it works for many body and even experimental data. And all the details are here, including aspects of some derivation. Thanks for your attention. And this is the work done with my students Harshini and postdoc Uday. Thanks.
Questions? One or two maybe?
So, I mean, for systems like chaotic billiards, this is also what this works?
Yeah, it works. Yeah, that's right. Yeah.
Both the like next one?
Yeah, right. Yeah. So, in fact, we tested up to 20th order spacing ratio. It works perfectly well. So, there are finite size effects, which is there in the paper that you will see, in the sense that as you take longer and longer strides, I mean, if you take higher order spacing ratio distribution, the problem is that your assumption that locally the density is constant breaks down. Okay.
No, does it work even for like chaotic billiards and all? I mean, and so you're saying basically numerically this is a much more efficient way.
Yeah, it's much more efficient. You don't have to do unfolding at all. Yeah, and yeah, that's right.
Yeah. So this results that you found the kth order.
Yeah.
So is that you can derive this, or is numerical?
Okay, so that's both numerical, and the beta prime has a derivation, leading order derivation. Yeah. So it's not completely proved yet. Yeah.
I just missed what is the analog of this Poissonian in the spacing?
So okay, I didn't have that result. So that can be exactly derived. So it's there in one of those papers. Yeah. It's a complicated form, but it's there. It's possible. Yes.
Okay, let's thank the speaker again.